So, good day. We will be looking at the sign of a timber beam using BS 5268, and let's say this particular beam spans 2.85 meter support and it supports a uniform distributed load of 10 kilonewton per meter, including the self weight of the beam. We want to determine a suitable section for this beam using timber of strength class C16 under service class 1. Assuming that the bearing length is 150 mm, this is the bearing length, and that the ends of the beam are held in position, and angle and compression edge held in line. So let's say we are assuming that H equals to 250 mm for the depth factor. So the procedure is very simple. Our distance between center of bearing L is 3 meters. That is, if we take the center of this place to the center of this place, that's this plus 150, because half of this is 75, half of this is 75. So 150 plus this, that's 3 meters. So now the grade stress, look at the grade stress and modulus of elasticity for C16. Now look at, these are the values we want to select. We select the bending parallel to grain, the compression perpendicular to grain, and shear, and modulus of elasticity. Now under this particular one, you can see that our C16 is 5.3 for the bending parallel to grain. So we write out each particular value that we will need for our calculations. Now let's proceed to the modification factor. Modification content does not apply since the beam is subject to service class 1. The duration of loading is 1. Load sharing factor does not apply since there is only a single beam. Then depth factor K7, which is we assume H to be equal to 250, so we put 250 here. Our H K7 will be something like 1.02. So for these instances, we'll be using K3 and K7. Others are not applicable for now. So let us look at the bending. The bending is very simple. Our normal bending is WL over 8 for uniformly distributed load. Since we have a 10 kilonewton here, and our L is what? Our L is 3 meters. So 10 times 3 over 8, we have it as 3.75 kilonewton meter. So the sigma m is equal to sigma m K2, K3, K7, K8. And I told you the right time that it is only K3 and K7 that will be applicable. So if we take that, we can easily calculate our sigma m, and 5.3 times 1.0 times 1.20 will give us 5.406. So if you can recall from our notes the other time, we said the calculation, after doing the calculation of sigma, the next thing is this one, which is our design moment, and for our design moment of resistance, we said with this one, so our Z will be equal to this over this, and then at the end of the day, we said we will check for permissible bending stress, and then we use this one to do the calculation. This is what we want to incorporate in the calculation that we are doing. So to incorporate this, we calculate our Z, this. So this is our moment here, we put it here. Our sigma m, we put it here, which is 5.40, we put it here. We have our ZSS to be this. Now our deflection, permissible deflection is 0.003 times span, and then we also said deflection to shear is likely to be insignificant compared to bending stress deflection, though I will still see that one later. Let us look at the normal deflection based on the calculation that we have here, that deflection for uniformly distributed load is 5/384 times this. So that's what we are going to apply now. If we apply that here, you can have 5 times this. These are L, W times L. Now over 384 EI. So from here, we can get, so since our dP is greater than or equal to dt, so since this one is greater than dt, our permissible deflection is greater than or equal to the total shear deflection. We can say this one, we can take this one as to be greater than or equals to whatever we have here. So we'll be able to get our second modulus of area, which is section modulus, which is greater than or equal to 673 times 10 raised to the power 6. Now this section modulus is what we will use in selecting our member size. Having gotten this, just like the way we did for steel, so this is what we are going to check. And under this particular section for table 6.8, where we have the section modulus of 60 second modulus of area of 67.3 is second modulus moment of area of 67.3. The one we will select, let me open the table. Section modulus 6.8. So okay, second moment of area. Now where we have 60 something, 60, you can see we have here we have 71, here we have 97.7. so we selected this, but we can still use 71.2 also now, but because 71.2 is greater than this, but it's very near. But to be on the safe side, that's why we are selecting this particular one. So we are selecting 97.7, and so from there we can calculate our ZSS, which is second modulus, which is 781, which is this, and then we can calculate this one. Our area is what, 10.8, 80.8, which is this. Just putting those values out, we can now write out our total deflection to be 5WL cubed over 384EI plus 12WI over 5EA. This is for a point load, and this is for uniform distributed load. So if we put our calculation together, we have our permissible deflection to be 9 mm, and then the one calculated here is 6.9 mm, which is less than the permissible deflection. So from there we can say, okay, this particular section is adequate. Then we can proceed to lateral buckling. The lateral buckling, the depth over b by width is equal to 5. So the actual member we are using is, the depth of the member is, since we are using 75 by 250, so we have 250 over 75, which is equal to 0.3, which is less than the permissible 5. So the section is adequate for lateral section. Also we check for the shear. The shear is so the permissible shear stress is TADM because of this. So we are using the appropriate K factor. So for this instance, we only need K3. So if we do the calculation, 0.67 times 1.0, then we'll be able to use we have 0.67 Newton per mm square. Now, so as we can see, the permissible shear stress is 2G times this, as I said, which is 0.67 times 1, because that one is what we select for this particular K3 factor the other time. However, somebody should ask, how did we get this 0.67? As I told you the other time, the timber that we are using is what class? We are designing to C16. This C16. Now under this C16, you can see the shear parallel to grain is 0.67. So this is where we got this one from. So I think that is clear on that. So 0.67 times 1, which is this. Then we calculate the maximum shear from the formula there, and then we have this, and then the maximum shear stress at neutral is 3FV over 2A. We have this, which is less than the permissible shear stress. So therefore the section is okay. Then finally we look at the bearing, permissible bearing stress. The same thing applicable. We look at this under the table. Then we have 1.7 times this. Then we have we check for the end reaction, F equals W over 2, which is 10 times 10 over 10 raised to the power of 3 divided by 2, which is this. Then we'll calculate this one out, and therefore the section is adequate in bearing since it's less than the permissible stress shear, bearing shear. Since all the checks are satisfactory, we use this one, SON to C16 beam. I think that is all on this particular one. Thank you very much.